when we want to describe the motion of an object, we can describe its position, where it is. We can describe its displacement, how far it's traveled. But if we want to really understand its motion, we need to describe its velocity. And its velocity is the rate of change of its position at a given instant. A rate of change means a time derivative. So our velocity vector is a time derivative of the position vector. But when you apply the derivative to a vector here that has components, that means that you are going to differentiate each component. The I hat, the j hat, and the k hat are unit vectors. Those are constants. And so those are not going to be affected by that derivative because they are constant. The instantaneous speed is the magnitude of the velocity. We've talked about instantaneous speed before in one dimension, and we said that it's just the amount without the plus or minus, without the direction in one dimension. Now, when we have a 2 or 3-dimensional vector, finding the magnitude is a little bit more complicated. But instantaneous speed is a scalar. It is always positive. The direction of the velocity vector is always tangent to the trajectory. It's tangent at every given point because the velocity vector is what direction you're moving at that instant. And at each instant, you're moving from one point on the trajectory to another point on the trajectory. And so you always have to be tangent to the trajectory at every single point. Velocity is velocity, and so it's going to be measured in meters per second or feet per second, as we've seen in one dimension. Average velocity is a similar idea. Average velocity is the average rate of change, and an average rate of change we've seen before is the rate of change during a finite interval. And a finite interval means a total displacement over a total time as opposed to a instantaneous displacement during an instant. They're related, they're very similar, but they're not the same. Whenever you see average, you should be thinking delta R, total change in position, over delta T, some finite time interval. But if the average velocity is delta R over delta T, well, R is our position vector. R has 3 components, and so we can apply this delta R over delta T in terms of its different components. Delta R is R final minus R initial. And we said that if you are subtracting 2 vectors, you can subtract their components. So the x component of delta R would be the x component of R final minus the x component of R initial. But really that just means the displacement in the x direction would be the final x coordinate minus the initial x coordinate, which is the definition of displacement that we saw before. We just have a displacement in the x direction and in the y direction and potentially in the z direction all at the same time. Another way to find the average velocity and really define the average value of any function is using the average value which you learned about in Calc 1. Another way to find the average velocity is to sum up the velocity at each instant during that interval, divide by the width of the interval, and that gives you the average velocity over the interval. Also notice that this quantity here is equal to the displacement. And if you have the displacement divided by 1 over t, that's this definition again. So these 2 definitions are just 2 different ways of saying the same thing. If we are integrating velocity vector, we're going to integrate it term by term. We're going to integrate it component by component. There's also an average speed. Average speed is the total distance divided by the total time. And the average speed, you'd have to find the total distance. You'd have to find that via the trajectory. So that is something that we're generally not going to deal with in this class because that math can get very complicated. But you could find this value the same as we've seen before in one dimension. You'd have to find the total distance and divide by the total time. And then lastly, we've talked about how to find velocity from position. We said that our velocity vector is the derivative of our position vector. And so if velocity is the derivative of r, position r, then r should be the antiderivative of velocity, That's kind of true. But whenever you do an integral, either you need a indefinite integral, which is going to give you a plus c, or you'll have a definite integral. This definite integral is looking at how, your speed times time, which gives you a displacement. In either case, you need an initial condition to get back to the original position. Your initial condition helps you find your plus c if you use a antiderivative, if you use an indefinite integral, or you need a initial condition, so you know your initial condition and your final condition. That allows you to find your displacement during this time interval. And then you use the fact that the final position is going to be your initial position plus how far you've moved to find the final position. If you find this, you know that. You need to know the initial position to find your position later in time. Again, this relationship is exactly the same as what you saw in one dimension, where the position x was the integral of the velocity, the x component of the velocity. Each one of these integrals here, you are going to break up into x and y and z components. And when you integrate them, you'll be able to just integrate them all separately. You can break, when you're adding multiple terms inside your integral, you can just break them up and integrate them separately. This term here is our change in the x direction. This term here is our displacement in the y direction, and so forth. So it's just like the problems you did before. In one dimension, you're just doing two problems, one in each direction, and those end up being the components of your overall value at the end.